logarithmic functions are inverses of each other. So they reverse each other, just like how inverse functions that we reviewed yesterday, you switch the x and the y value. Exponentials and logs are a little bit different because if you notice, your variable is located in your exponent position, so it becomes very difficult to switch these two. So we have a way of rewriting them using logarithmic functions. When we studied it, we called it rolling the log, but using Desmos will graph these, and you can see the equivalency or the inverse based off of the symmetry around that y equals x. So like when we talked about folding the graph, where if we were to take this function and we were to fold it, it would look something like this. And that's what we see with our log function, and vice versa. If you have an exponential decay, if we folded it along that line, it would look something like this, which is kind of what we get over here. Just very messed up drawing. What we focused primarily on was this growth and decay when it came to rates and doubling and half-life. So if you remember that rate is how quickly something is growing or how quickly something is dying, and when we are presented with that, we're usually presented it as a percentage, and we have to turn it into a decimal. That is very, very, very important. And just a reminder, if you have a percent, say 7%, we just move the decimal place over twice, fill in any holes. Also, if you use Desmos will convert that for you. But if we are dealing with something with a plus sign, then we know that it is a growth. And so I had one student one year decide they were going to use visuals. So they said if all of this put together is greater than 1, it's a growth. If all of that is less than 1, then it's a decay. Or if it starts with a 1, it's a growth. If it starts with a 0, it's a decay. And then we do have your principal value. That's what you're starting with. You have your rate as a decimal, and you have to do something over and over and over again for a specific amount of time. And so instead of memorizing the formula, what we do is we kind of talk our way through that. So we say, hey, I have to start with something. I'm going to grow it or kill it off for a very, very, very specific amount of time. Or I'm going to keep doing the same thing over and over and over again. Compound interest says that we're going to keep doing that over and over and over again, except we're going to be very specific with the amount of time in which we look at something. We called that monthly, quarterly, things like that. And that is the number of times that you actually look at it. So these two formulas are very, very similar. The first one says, I don't really care when I look at it. And the second one says, yes, we do. We're only going to look at it for very specific amounts of time. One thing that shows up on the EOC a lot is this doubling and half-life. And essentially, it's exactly the same formula, except that instead of when you double something, you take the original 100% and you add to it another 100%, and you get out 200%, which is where the 2 comes from. And that does take an amount of time. And so we just say how many cycles is that going through, and the same thing with half-life. They do show up, and you can do these just using a table. So a lot of times when they ask you to solve for something, or what is the doubling time, how long does it take to double something, if you build a T-chart, if you're panicked, you can build a T-chart and you can just double these numbers until you get what you need. So there are some options there. Overall, though, these are the major topics that come out of Unit 2 in terms of exponential growth and decay. Again, they're going to focus primarily on money or population. So how quickly is a population growing, or how quickly is a population decaying? If you look at the back of your study sheet, there are 13 questions. Most of this can be done using Desmos. So if we look at question number 1, it's asking you, is this a growth or decay model? So if we're looking through these numbers, are these values growing or decaying? Meaning, are they getting bigger or are they getting smaller? They are getting significantly bigger. If you're somebody who needs to see that or just double check, you can use Desmos and you can recreate this table in Desmos. So 0, all I'm doing is just entering the data that they have given me into my table. 2048. If I hit the little magnifying button next to my table, it will auto adjust for me. And I can see that those points are increasing. They're going up, which is a growth model. And then the following B and C are asking me like, hey, what's the base? What's the y-intercept? What are they counting by? So base is another form for like, where are we starting? So we're starting with 2's. So I do have a base 2 and my y-intercept is also 2. I can look at the graph and also pick that out. Okay. The function, if we have a table, you can use the little function button on the side of the table, and it's going to give you all of these options that you can use to create a function. Well, this is an exponential function because it does have that slight curve, but you can go through and you can kind of select them as you need to until you see which one lines up well. Well, that lines up well, but we haven't studied quartics. If we look at exponential, this one lines up perfectly, and your function is given to you right here at the bottom of Desmos. Make this a little bit bigger. Right there in Desmos is your equation, and so my function is y is equal to 2 times 4x. Okay. All of this information, this b value, all of that, you don't need to know that, okay? You could just read a table, and 9 times out of 10, they're not going to ask you that on the EOC. Okay. They are going to ask you to write some equivalent statements, and we called it rolling the log. So we would start with our base. Our base was 2. We would roll under the equal sign and then over the equal sign. So it would look like 2 to the 5th is equal to 32. Again, here, well, I don't have a base. I don't see a base, so it's an automatic 10. So we start with the base under and then over. So -1 is equal to 1 over 10. And then vice versa. You can go, you start with your base. So this one you have to have a log because it says write in log. So we're going to start with our base, and then it is under and over. So 216 is equal to 3. And you can also double, triple check. So here under functions, or you can type log, L-O-G. You're going to find it near the bottom. Okay. Log base 6 of 216. You can see that it equals 3, the same way that 6 raised to the power of 3 should equal 216. So there's some ways to check that. Again, start with your base, so log base 64, and the rule is always under and then over. These will show up. They'll ask you what's the inverse function. They'll ask you which statements are equivalent, those kinds of things. Evaluating, very, very, very basic. This is straight Desmos. You can put the whole thing in Desmos and it will spit out a value for you. So you come right in here and you say, let me just clear that out, log base 3 of 27, and it will give you those values. So I think that like these are give me points, like just give me the points. They're not difficult, but students do struggle with like which log to choose. So if you're looking at your options, you have one with no base and one that has like a little number down there. So you just have to look and say, okay, I'm going to need a base here. I'm going to need a base here. So when I'm coming in and I'm choosing them, make sure you choose the one that's got the lower base. If you like to type it in, an underscore, if you click the underscore, it puts it in for you. 625. And this comes out to, now look at this. This is a decimal. But if you look to the left in the blue selection bar, it does have a fraction. You can click that and it will automatically turn it into fraction form for you. And the last one, log base 16 of 64 is 1.5, or it can be turned into 3/2. So Unit 2 focused a lot on just converting back and forth, but the skills are available for you in Desmos. Yesterday we talked about this one. This one's a little strange. It is a find the value of x, and it has an equal sign, and we love equal signs because that lets us split it into two equations. And we can graph to solve. So y is equal to 100 to the power of, now notice here, if I try to put the whole thing in, it's going to want to drop my plus sign, and it's very aggravating. So anytime that you need things to stick together, we can lock them up in a set of parentheses, and that means that those exponents aren't going anywhere. So if you get really aggravated, just know that that's why. Okay, and I can't help you on test day. So y is equal to 1 divided by 1,000 raised to the power of, I want to keep all of this together. So raised to the power of 2x plus 3. And I'm looking where my blue and my red intersect. They're going to zoom out. Is there a place where they come together? It's going to be way, way, way up there. But essentially we're looking at where they intersect, if they intersect. This one is, they do intersect. It's just very difficult to see. I do know that this, using my exponent rules, can be written as 1,000 to the negative 1. So if I wanted to, I could come in here and change this. Let me see if I change it, if it's going to make a difference. On the check-in, they're only going to give us things that work. So we would just keep going using our answer choices to, oop, there it is, right where they crisscross. Again, you could have done it if we kept it the same. I just hadn't zoomed out far enough. Oops, there we are. There's that gray dot. It does say the x value, so negative 2.625. So again, you have to see, you have to zoom out a long time to be able to find those answers. Same thing is true with number 5. It has that equal sign, so we do get to split it into two different equations, and we're looking where the two crisscross. So y is equal to log, and it has a base 4, so I need to pick the one that's got the base. Log base 4, x plus 2 minus 1. Y is equal to 5. I'm going to hit the house button on my Desmos to recenter everything, and I can see that the green and the purple are going to have to come together eventually. So again, just zooming out till I find where they come together. There's that gray dot. Okay, it's very far out, and that's okay. We've got it all. Oops, I missed a whole number here. Let me go back and fix that. A 3. Maybe it's not crazy. Make sure you have it typed in. As you can see, I still make mistakes, so double check your work. 14 seems a lot more reasonable. So we're honestly just using Desmos to do anything that says solve, find the value of x, any of that. is going to be Desmos, Desmos, Desmos. This one was Desmos. Number 1 was Desmos. All of 2 and 3 are Desmos. This one's 100% Desmos. So looking at, not necessarily being perfect or having to memorize things, but we're in test-taking mode, which means we have to approach this from a test-taking perspective. Okay. Number 6 says, given the following function, find the x-intercept. That is a vocabulary word. And we did learn yesterday that f of x, you can still type that in. Desmos, if you want to change it to a y, you're more than welcome to. But f of x is equal to 3 minus 4 to the power. I need to keep all of that together. So x minus 1. I am looking for the x-intercept, which is where it touches the x-axis. And that is, it says round to the nearest 10th. Okay, you guys low-key still struggle with rounding. So the 10th has a 1 0, so I need 1 decimal place. So if my answer is 1.79248, I'm going to look here. This is what I need. I look to the guy behind him and I say, does it stay a 7 or does it get an upgrade? Any 5 or more, raise the score. So this does get an upgrade to 1.8. Okay, so careful with your rounding. When I looked at your check-in scores, a lot of you did great work. You just rounded badly. These ones, we don't care about transformations. We're not required to study those. Okay, I'm only going to do 1. I'm going to do 7. I'm going to skip 8. But I just want to talk about this in terms of domain and range. So f of x is equal to 2 exponent. I want to keep all the stuff together. So x plus 5 minus 2. Make sure that my Desmos looks exactly like my question. It is asking for an asymptote. Remember, asymptotes are places we don't touch. We do not touch other people's asymptotes. That is inappropriate. And so if I'm looking at my image, this is where it flattens out and will not touch a certain area. And if I'm looking, it is a horizontal asymptote. So it goes flat at the bottom and it goes flat around the value. I'm going to zoom in until it's appropriately scaled. There we go. It zooms out. It flattens out right in here is where it flattens out. And that is at the value -2. So it has a horizontal asymptote at -2. If you need to just double, triple check, you can always graph them and you can see, oh, look, it kind of goes flat right about there. I'm going to change this to a dashed line so it's easier for us. But we can see that the blue is an asymptote and our graph is curvy. So she has an asymptote. And it flattens out right there, so there's where the asymptote is. Domain is all your x values, so if I keep zooming out, it will forever touch the left, and it will go all the way to the right, so from -infinity to infinity, or we say all real numbers. But I do want to look at the range. Remember, range is like all your y values, just like, Drake started from the bottom, now we're here. So we start from the bottom and we say, what is going on near the bottom of my function? I notice that it's flat. It's flat at -2 and it is an asymptote, so we don't touch it. So it gets a parentheses and that graph will continue to move in an upward direction infinitely. So my range is from -2 to infinity. It may also be written as y equals -2. If you do not like this notation, and many of you don't, just check it in Desmos and say, oops, I missed my -2. Is all of my red function currently covered in green shade? The answer is yes. Okay. If you're struggling with your signage, just double check, flip your sign and just see. And if you have it the opposite direction, you'll see that it's shaded, but there's nothing there. So you can see, okay, I need to make sure my sign is correct. So I know a lot of us prefer notation, interval notation. We do have to know that inequality one. This is exactly the same, except it's a log function, graph it. This one, you have two functions, and we talked about it yesterday. So we're not doing, some of the skills that we have from yesterday are going to roll over into every single unit that we do. F of x is equal to the log, and I need a base 2. So log base 2 of 4x minus 5, and g of x is equal to log base 2 of 7 minus 6x. And I'm looking where the two are equal, which means I'm looking where they crisscross, and my value for x is 2.4. So anytime we have like a solving question or a where are they the same, we're just looking where they crisscross. Here's where our formulas start to come in, and I'm not doing all of these. I'm going to pick a couple. Okay. A scientist has 260 milligrams substance that has a half-life of 22 days. How much of the substance does the scientist have left after 6 weeks? Well, 6 weeks is 42 days. Okay, so when we go to set it up, if we talk our way through it, it's going to say we started with 260 half-life, which means that we are halving it. We are going to take a look at it for 42 days, but every 22 days is when it gets cut in half. So looking at those different cycles. Okay, pop that sucker right in Desmos. We are not doing anything fancy. 260, it is being cut in half. We are going to look at it for a total of 42 days, but it gets cut in half every 22 days. So after 6 weeks, there's only 69.2 milligrams of whatever substance the scientists decided that they were going to study. All right, if you decide to deposit $1,600 in an investment account with 5% interest rate compounded quarterly, okay, what this means is that it's earning interest. Somebody's going to open up that account every quarter, and every time they open up that account, the interest hits all at once. That's kind of how we think about it. Okay, how long will it take for your money to double? So if you started with $1,600, we want the final amount to be $3,200. So we want $3,200. We're going to start off with $1,600. It says it's compounded quarterly at 5%. So it means the original 100, that's where the 1 comes from. Okay, it's going to grow at 5%. So 5% is a decimal, right? Is 0.05. Quarterly, so we're going to take our rate and split it up into 4 times a year. We're going to look at it 4 times a year for a certain amount of time. We don't know how much time. I've got an equation. I've got an equal sign. So y is equal to 3,200. That's what I want to finish with. Y is equal to 1,600 is what I started with. I'm going to grow it by 5% every quarter. And I'm going to look at that 4 times a year for a certain amount of time. And I don't know what that time is. I'm going to zoom very far out where green and blue come together, get a good idea, zoom, zoom, zoom. And it is going to take me 13.9 years. My opinion, not a very good investment. If it takes you almost 14 years to double your money, that's not a very good investment. Let's see. There's that doubles. Okay. Asher is working with a particular bacteria that doubles every 3.6 hours. If he has 38 bacteria initially, it's going to double. Then how many bacteria does he have after 16 hours? So what we're going to look at is 38 bacteria. They're going to double. We're watching this bad boy for 16 hours, and it's going to double every 3.6. And that's a straight calculator question. 38 bacteria doubling. We're watching it for 16 hours, but it's going to do its thing every 3.6. So after 16 hours, we have 827. That's not how you write that number at all. 827.4 whatever bacteria. And it's a bacteria. So we can't really have zero point 0.4 bacteria. So again, this is the conversation of, does every bacteria count? So it could be 827 or it could be 828. So either one of those, most often it's going to round like a normal number, but just know that there's some conflict in there about what counts and what doesn't count. Gooey. And the last one has to do with interest again. This is compounded continuously. They don't really ask those questions too much. But this is just like the nitty gritty. This isn't everything, it's just the nitty gritty. But if I look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 11 or 12 that we did are all Desmos. The word problems are the only ones that require you to use a formula. So we don't have to memorize a bunch of stuff. However, if we talk our way through those, then those formulas become natural to us. So you've got the front page. I've got the formulas all written out for you. You can use those. You can write them down. We're going to do a brain dump on Friday about all the things that we should know or shouldn't know on the exam. If you can get this one, that growth and decay one, you'll be just fine. So practice, questions on the back, study on the front. And then I have an assignment posted in Waygrounds just like yesterday that you're going to work on today.